up, once it finishes all of this, then it should be good to go. You can just check it once before you close it down. I think captions. Okay, so hopefully there's things now. Looks like there is. And that should be up. So once it's up, you can close the tab. You don't need it anymore. Okay. And then it's casting already.
So we present using that.
Yeah.
Okay, much easier.
Yeah, then we just have one thing. So if you use slideshow mode on Google Slides, I think most of us know, but you can use, I think, the L for laser pointer, right?
Okay.
And then A to go back to arrow. Oh, sorry, not A. What is it? Forget which one it is. Yeah.
So like Microsoft Word unfortunately.
Yeah.
And
Keyboard shortcuts. Okay, so
or mean go backwards, is it?
yeah, to get out of laser pointer mode.
Okay, so
Yeah.
you added me as the co-host for Fridays.
Yeah,
So,
that's a good idea. I will do that now.
okay.
Yeah, on the other laptop because we're going to start. Okay, so everyone, welcome to today's session. There are going to be some announcements first, so that we know how group projects and everything are going to go. Okay, and because on Friday we have our normal session downstairs, but I won't be here. So Yi-sung, who is leading the lecture organization for week 4, will be helping out. Okay, so today we have all of our speakers for week 3. Of course, because it's a makeup, unfortunately not everyone is available. So some of our lecturers pre-recorded their segments, and I think our coordinator Warren will be helping to play those segments. And then again, we are going to stop once in a while to talk about the output and questions that we have about this. Okay, so a number of you are already on the deck, but in case you don't have the deck, again, you can go to week 3 dash prep and get the slides there. It follows the same naming convention as always, which is bit.ly CS6101 term 2310 dash week 03. And I hope many of us, not just the support team, but anyone who's interested in active listening will also go to the zero-shot prompting and zero-shot inference page for scribing. Okay, as always, we'll try to spend 1 week post-lecture to make things pretty enough that we're happy as a team to make sure we finalize it and make committed to read-only mode. Okay. Okay, I wanted to talk a bit about projects. So one of the things that we should be clear about is that everyone in this organization for this course needs to do a project, okay? Especially our undergraduates who are doing it for project credit, and especially also for our 60, can somebody help open the door? 6101 students who are actually doing it for first year PhD student credit. So I believe there are 3 of you who are doing it for credit for our PhD students. Okay, so the PhD students doing lab rotations, any of you here? Okay, 1 of us, okay, 2, okay. Then you have to make sure that you have decided a project that has at least around 60 hours of work, right, in total. Okay, now you might be wondering, for everyone, how do you check that you're doing the project correctly? Okay, so I'm going to share this with you now. Okay, in our Slack workspace, in the general channel, there is our normal Google Sheet, this one here, right? Okay, in fact, let me try to turn this. Oh, it's not. Okay, never mind. This sheet here. So if you go to that sheet, okay, which is our usual sheet with all the colorful things, all right, you scroll, you'll see another set of columns that I added this week. Okay, so I'm going to blow these up for you so you can see what it says. Okay, all right. So there are self-assessments that you're going to fill out. So for example, Victor, I think, is one of the lecturers this week. So he's going to click on number 3 here to say he did one segment of lecture one. So if you did segment one, you were the first speaker, the second speaker, first speaker, fourth speaker, click on this. Okay, this is for you to tell me that you accomplished your lecturing duty. Okay, same for your support role. So for example, if you were the coordinator, like Warren is the coordinator this week, then he would click on this for his role. If you were busy for Kahoot, that's going to be played next week, or one of the scribes or scribe finalizer, you can do that. So for example, if you were in charge last week, week 3, or you helped in week 2, you can also put this down. Okay, so that's one thing that you'll do. So you need to do this for the segment of lecture that you are doing for 6101 for lecture 1 and support role 1. If you are taking for 4 MC credit in CP 3108B for undergraduates, you need to fill out all 4 of these columns. Okay. Our wing members who are from my lab, unfortunately, you guys are compelled by your professor to do all 4. Okay, but NUS students in general don't have this problem or feature. I guess I should advertise it as a feature. Okay, now for projects, okay, so projects are over here. You don't have to touch this column. In fact, I'm going to color it later so that it's clear that you don't have to, it's just a sum column, as you can see, okay? So you can use this to track how many hours you've done in total towards your goal of meeting the project, okay? So you can say, for example, oh, I spent 5 lectures preparing for lecture 1. I just talked to Lawrence. He said he spent 20 hours. So then he can put 20 in his column here, okay, into the cell for him. Okay, same for the other ones here. So, okay, you can fill in those rows. Again, for those of you who are just doing it for the first half, or who are external guests, you only have 1 role. You only have to be prepared for 1 lecturing role, 1 support role. So these 2 other columns you can leave as 0, right? Support role 2 and lecture 2 hours don't need to fill in, okay? Those of you doing all 4, 2 lectures and 2 support roles have to fill out all 4. Everyone clear about that? Okay, pretty straightforward, okay? For projects, this is self-declared. Okay, so I'm not going to check you. I want you to minute it yourself. Okay, it's good idea for you to think about your availability during the semester, because especially for our internal NUS students, things get busy after week 8, especially if you're an undergraduate. Graduate students, it doesn't matter. You're generally free between 12 midnight and 6 a.m. Most students are like that. Okay, so it's up to you. All right, you can track. All right, so what it says here is you have project hours for the first 4 weeks, right? So week 00, which is already passed, to week 04, which is this week, okay? Project hours for the next weeks, okay? 05 to 07, and that will mean all of the students, the 2 of you here who are 6101 for the first half, you will need to do project hours for that. Okay, you may not be finished with the project in that amount of time. That's okay. All right, you can take longer to do your project. In fact, I encourage you to do projects not just within that time period, but to do it with a larger group of people. You can fill in other hours for the 3rd, 4th, and 4th. Okay, so hopefully that will total the hours on the projects. You have miscellaneous hours that don't fall under project work that have to do with coordination or background learning or whatever, you can fudge it, okay? So this is your fudge column. You can put whatever you're in here. You put 70 hours, I will come back and ask you why, okay? But otherwise, it's fine, all right? It's again, this is pass-fail course. It's not meant to be hard on you, okay? It's meant to be an opportunity to self-study. So it's up to you to decide how you want to do this, okay? Everyone clear about this? All right, when you've done all of these things and at the end of the semester, you have a total that matches somewhere around 60 to 120. Better would be 70 to 140. Okay, somewhere around that. Then I would just check, you've checked the box. I will let you pass the course. Okay, there's no grading. Okay, it's just that you try your best to learn as much as you can about large language models and practice it. Any questions about these formalities? Okay, pretty straightforward, right? Okay, I want to spend another 2 or 3 minutes talking about what we are going to do for projects. Okay, so I have to blow this up because it's tiny. All right. So if you go to the project channel, it's not necessarily directly inside of your channel browser. So you need to add it if you haven't already put yourself in. Okay. You are going to use the project channel for a number of different things. Okay. So I'm going to try it. Yep. Okay. So we will have 5 sprints that you'll need to report in. Okay. And we are not going to do it within class, okay? But every 2 weeks and every 1 week for those of us who are only in one part of the class, for example, our 2 students here today doing 6101, okay? For the first half, you need to fill out a sprint chart, okay? So I'll take a look at this and there are directions inside of each part, okay? So for sprint ideation 1, which begins this week, okay? You need to fill out this deck. You need to take this Google slide deck, copy it to your own file, and then share it back to this group, wingnus.gmail.com. Okay, so that we have access to it, okay, and that we can save it for posterity. All right, so that other people will have examples of this. All right, what does it say? Delete this slide, fill out the metadata. So for example, change the project title, change the team members, okay? And tell us whether it's okay to archive this slide deck or not. You don't want it public, that's fine, okay? If you don't mind it being public, then we will save it and then other people can refer to it later, okay? Like for the next semester, they want to see what projects you did, then they can take a look, all right? For this sprint, it's very easy, okay? You can write an abstract of what you think you'd like to do. If there's an academic paper or a model that you're going to use, you can declare all of these things here, okay? So I have a particular paper that I want to replicate. There is a GitHub repo that shows us how to use it. There's a data set that I thought I would like to try it out on. It could be an internal data set in my organization. I just write it there. It doesn't have to be public. And some notion of what an evaluation metric would be, okay? Okay, you're free to permute this. This is sort of your standard implementation type of project. Okay, again, for 6101, we just want your experience. Okay, even though this is a university and we care more about research projects, you don't have to go that direction. Okay, on the project channel, okay, there were cases of things that were research directions. So these are all from Michael's slides in week 1, right? So alignment, being able to apply LLM to a task, open world, large language models, understanding an LLM's capabilities. Here are some other ones that are not necessarily anything to do with research. They're just application areas. Those are absolutely fine too, okay? For our undergraduates who are not so keen on doing graduate work, okay, because you're scared of permanent head damage, fine, no problem. Then I suggest you do an applications-oriented project, okay? There are too many people in this world right now looking for large language model experience. So again, if you do this type of project, you come to our reverse career fair, which you are all supposed to do as part of steps in week 13. I guarantee you somebody will come headhunting you, okay? There's no, I mean, maybe even within our own group, people would like to head on to. Okay, so there are lots of different projects that you could do. These are just smatterings of things that I put up, and you're welcome to look at them. Okay, there were some questions about group size. So again, there's no limit to group size. I think it's good that we try to array ourselves, that we internally network here. We have lots of people from all walks of life, from high school students all the way to seasoned veterans in the software engineering and AI world. And it's good to meet each other. Okay, so I take that as a way to do that. Okay, but again, we don't want any social loafers. We want everyone to have time on task, experience with large language models, even if it means just doing in context demonstration, right? Because sometimes the fine tuning and all of this takes a lot of CPU, GPU. Okay, so you will need to do these. You can read the pin post here, okay, that tells you what to do. Okay, so I'm going to just read this. People, especially undergraduates, when they first come to do projects, they think very big, and that's great. But the execution is very hard. Okay, all of us know that debugging code takes up way too much time. You thought, okay, it's going to take 20 minutes. It took you 12 hours to debug because you had to install a project. Then you had to deal with dependencies, outdated things. And then when you finish debugging everything, finally, I can write my code. Okay. So that's why it's always good to start very small. Start with something easy to replicate and go from there. Okay. You can do lots of different types of things. In fact, even not doing code, even just talking about it as a science communicator is a useful project. Okay, so you can do all of these. Now, again, I've put up 5 decks here. Please click on all 5 of these to see what's expected of you. Okay, and there are ideas about what you should be doing at each stage. So the first one is ideation. Okay, I've already showed you what that looks like. MVP. Okay, minimum viable project, replicating a paper, okay, maybe just running the Python notebook so it runs, okay, on a GPU cluster or NSCC if you have access to that, okay. Extension, okay, some of these codes have bugs, some of them you might want to extend in some way, okay. Then doing your core project, okay, and then some type of evaluation, and then finally, at the end of the entire course around week 13.
Screen share.
Okay, sorry, screen share. There's somebody outside. Okay, sorry about that. Thanks for telling us. Okay, so it's pinned here in the project channel. Okay, there is evaluation and dissemination. So in week 13, we will have steps, and then everyone is obligated to go there Wednesday afternoon to evening to show off their project. Okay, any questions about these? Okay, so we're all clear what to do. You can go ahead if you're assigned some work in the past couple of weeks to go to the slide, the deck. Okay, and then go ahead and check out these parts. All right, so I've said, for example, this week I've done, if I was part of lecture 1, then I would say, which segment am I doing? Am I doing the first segment, third segment, etc.? Okay, and I can fill these out. All right, so I've already taken 15 minutes of time, so we're not going to do that any longer. I think Warren is ready. Yeah, we're going to do Kahoot first. So let's go do Kahoot. So Yisong, you will have to do the same on Friday. Anyone not in yet?
Yeah, I'm not in there.
Okay.
I'll catch up. It's on 7 months.
Yeah, we'll wait. It's okay. Okay, again, so everyone, when you're doing your support role, you can consider doing the Kahoot. That means, again, you revise what was taught in the lecture. You create the Kahoot using the credentials that are pinned on the general channel. And then you will create the Kahoot and then we'll run it the following day. Hey, everyone in? Anyone else? No? Hey, let's go. So whoever created the Kahoot can narrate it. So who created the Kahoot? Okay, Lauren.
First question is, the model is a question. And then why do we adapt the language models? Because you wouldn't want to improve performance. Like when I mean performance on pre-trained data, it doesn't mean like improving performance on downstream tasks. I mean like for the language modeling task, improving its performance using adaptation, which is generally not the intention of it. You want to use adaptation to improve the performance for like downstream tasks. So therefore, like the first two are correct. Prompting might not work for specific tasks. Therefore, we adapt the model to make it better for like downstream tasks instead of using prompting. And then the vanilla LLMs may not be as performant on like specific downstream tasks like medical like transcription. So therefore, we want to adapt it to perform better with the domain relevant data. So therefore, it's the red and yellow one. Then also for the blue one, I mean like you can give that as a reason to put your adapter model on Hugging Face, but I mean like there should be something more like than that. Like that's a very superficial reason. If I didn't put this answer. Yeah. I think go to the next question.
Okay, so Warren, you can run the laptop over here if you don't mind.
So like Clyde is like the first right now, and Hong Yao is the second, and KT is third. It's great. Yeah, okay, thank you. So like we're gonna see. So how is probing best described? So probing is more of like a method to understand representations of language models, because like this is what was seen in the slides firstly, and secondly, it's also because when we talked about it last lecture, it's using it as like some sort like you have language vectors, and you really want to use probing, right, to determine whether an attribute exists in whatever vector you have. So the other answers are wrong, right? Because number one, when you say it's used to detect current like emitter, right? We use the analogy of an emitter last lecture to like describe what is probing, but however, it's not exactly the same as the emitter. For the yellow one, it's not really an attention layer. Usually we use like linear layers instead of like attention layers to actually do probing, and it's not really encoding outputs. You're trying to just classify something based on whether it has an attribute. Then for the green color line, right, it is totally wrong. Like the green color one is not even what probing actually stands for. So yeah, those are the explanations why. So it seems that Clyde is still first, and the podium hasn't changed. So the question is the true or false, and it asks whether probing introduces adaptation without introducing new domain knowledge, and does not tune the original LLM's parameters. So the answer is true here, right? Because it really is like a classifier here, to build on to the previous explanation, right? It's just a classifier head that determines like it detects an attribute. So it doesn't really introduce any new domain knowledge. You're not really fine-tuning on new data. And secondly, right, you do not fine-tune the original LLM parameter. You actually add like a new linear layer as a classifier head to when you use probing. Therefore, it's true and not false. So yeah, on to the next question. Yeah, now we have a new.
Agree with that? Do we all agree with that characterization? Yeah. Anyone who wrote false that wants to bring up any issues about this?
Or check the chat.
Yeah, you can check the chat.
Never mind. The chat doesn't have anything.
Okay.
So if not, I'll just continue the next question. So next one is just why is fine-tuning language models important?
I don't know.
It looks expensive.
So the answer is yellow because like for blue and red, right, those are really nonsensical answers. For green, sometimes like for fine-tuning language models, right, there's nothing to do with making the model run faster. If you want to do that, there's other methods that will actually do this, but this is not like the main focus of fine-tuning. Usually fine-tuning, you want to improve the performance of the LLM on like a downstream task, like let's say like sentiment analysis or a different task. And therefore we want to do fine-tuning because our pre-trained model, our pre-trained data may not have like it may not have the same data distribution and therefore have like represent like your downstream task properly. That's why you want to fine-tune in order to make it more performant on downstream tasks. So yeah, does anyone
Everyone got this, so I mean,
okay. Yeah, our podium is still the same. We'll go to the next question. This is a multi-site. And what's the differences between FLAIR and T0? We actually covered this in the lecture as well. The actual answer is all four. So firstly, right, like the red color one, I think we went through this the last section. It was very interesting. Is that the T0, like one of the differences between FLAIR and T0 is that T0 was trained with a diversity of prompts, and they use that to actually evaluate whether different prompts have the effect on like the language model. Then if in FLAIR, right, prompt templates are like a fixed, just fixed to like a certain prompt structure. Then for yellow, T0 does hold on multiple data structures when it does its multitask like learning. However, for FLAIR, right, you need to hold on a single like cluster when it does its training. Then for T0 and FLAIR, the blue color one, this one is a bit hard, but yeah, they were made by different organizations. So T0 was made by Luther and a few other universities, while FLAIR was made by Google. Then the green color one is that performance on the held out task after multitask prompted learning, right? There's a difference between FLAIR and T0. FLAIR actually had a decreased performance after on the held out task after multitask prompted learning. However, for T0, because they're using a diversity of prompts, right? I think that was one of the factors of why they actually did better. So yeah, does anyone have any questions regarding this one? Because there's a lot to unpack here, I think, this question. If not, I'll go on to the next one.
sounds good. Ooh.
Oh, we have a new new underdog. Yeah. This is also another multi-select. And what are the components of like RLHF?
Mash your buttons quick.
It's not multi-select, it's multi-select. Yeah, so actually the yellow color one, right? Everything is correct to the yellow color one. And this is just a very small terminological like detail to trick people out. But why is it policy and not preference? Right? Because in reinforcement learning, we want to have this thing called a policy that we will use want to maximize the reward. So we actually take terminology from that, and then therefore it's called proximal policy optimization, because it is a reinforcement learning by human feedback and not preference.
Right.
Oh yeah, we shifted again. So now Clyde's first again. So this one is going to be a true or false. RLHF does not decrease the performance of the
Very quick.
Yeah, so I see it's going to put true, and the reason why this is not true is because it does decrease the performance of the model. So there's this thing in RLHF called alignment text, and there's someone there. They haven't opened the door. I think there's someone there.
All right.
So like just as I was saying, there's an alignment text in reinforcement learning by human feedback, and just explore in the Instruct-GPT paper as well as I think one of OpenAI's GPT-3 papers. So when you train like a model using reinforcement learning by human feedback, right? I think what happens is that because you're shifting the data distribution by a bit when you train on reinforcement learning, actually causes like some of the performance of the model to drop as well, because you're sacrificing some concepts for the sake of alignment to make it so there's more, it outputs more friendly outputs. So when you do that, right, you are shifting a bit, and therefore some of the performance actually drops. It's unable to express itself as clearly as before without all the alignment. So we call it alignment text, and therefore it decreases the performance of the model.
You guys, there's plenty of space at the desk and it's fine. You guys, especially if you're holding a laptop, don't fry your lap. Come up to the front.
So yeah, now we have a. I'll just wait for you to shift first, then I'll just. So yeah, let's go on to the next question. Oh, is this the? Oh yeah, so this like what are some examples of parameter efficient fine tuning? So yeah, actually it's the red, blue, and the green one. So for the yellow, why is it not model pruning? It's because model pruning is not really fine tuning. When you do model pruning, right, you're trying to cut down on number of parameters in the model so as to make it smaller so it can fit on a GPU or for other tasks. So that's not really fine tuning, but more of just making the model smaller for deploying it on like other instances. So we don't consider model pruning as parameter efficient fine tuning. On the other hand, the other three actually is parameter efficient fine tuning, because for the red and the blue, right, when you do prompt and prefix fine tuning, right, you're trying to insert like additional info into the prompt itself. Then for prefix tuning, it's the same as prompt tuning, but you're also doing something with the attention values, the key and the value. Is it the key and the value, right? Or is it I forgot whether it's Korean key or key and value. But some of the attention layers, right, you're doing some sort of like modification on that as well, so as to ensure that with all these inserted like additional prompt, right, the model actually is able to fine tune on a certain task without actually without actually like really fine-tuning natively, where you have to fine-tune all of the parameters model. You just fine-tune based on like the small little like the additional appending of the prompt. So for those two, it's called, that's why I consider it under parameter efficient fine-tuning. Then for like lower adaptation, right, this one is more of like you're trying to reparameterize the weight matrices as like two smaller like matrices. Then from there, you train these smaller matrices and then combine them back together to fine-tune. So when you do this kind of reparameterization into like smaller matrices, you're using less you're using like less GPU memory, because you're not really fine-tuning for example 8x8 like matrix. It can be, for example, 8x2 and a 2x8, and that actually has only 16 compared to 64. So you can see there's a very big difference, and therefore it's also considered parameter efficient fine-tuning.
Okay, we've got a final question. Let's see how we're doing in this semi-finals.
Yeah, the last question to be the hardest. Oh yeah, Conrad has reached the
We have
top.
our two first place vying neck and neck.
Yeah, the last question is make or break. So it's really talking more about the frontier, and you can explore these papers later. So these are recent developments in RHF and alignment, and basically these are papers you can, yeah. So yeah, actually everything is correct. So all these are new papers, and the most of these questions is not really to like really grill someone, but it's more just to like show you guys like some papers you can actually explore after the previous lecture to really like deepen your knowledge. So here are some of the papers that you can read. So yeah, let's see the final podium. So can I go third place?
Oh,
Nice.
And number 2 is Hannah. And first place is
we have a dark horse. My goodness.
correct.
I have Warren to get some content. Yeah.
Also, how do I go to it? So this one.
Yeah, it's a little hard because all the Zoom windows.
Yeah.
It's
Control the view. Command the view. Okay. Okay. Alright. So, Prof, then you're using this computer to share the recordings, right?
Yeah, that's right. Okay. So I think we'll get started on today's part. Is that the right?
Yeah,
Is
I
that
need
the
to
way?
skip the slideshow for the recording portions because
Sorry?
when I go to the recording portion, maybe to skip the slideshow just to show because I think it
Okay,
only
yeah,
works.
yeah. You can help with that.
Okay.
Is the first one a recording?
No, yeah, this is recording, so I'll just do that later.
Okay,
So
yeah.
hi everyone, so I'm Warren, and then this is the lecturing team for like today. Today's topic will be on prompting and zero-shot inference. So our lecturers will be Esther, who will talk about what are prompts. Victor will talk more about what's in-context learning. Richmond will talk about few-shot and zero-shot learning. And Suveen will talk about chain of thought. Then Lawrence will have like a very good lecture on both self-consistency as well as tree of thought and graph of thought. And lastly, I'll cover React, which is another prompt engineering technique. So the first one, which is about prompts, will be in this video link. Let me see if I can access from here. Sorry. So I can't access from here. So I will go out and then I will check this video. Yeah. Because Esther's not here today, so we'll be using her video on YouTube instead. Let me just
Prompts.
let me just restart.
Hello everyone, my name is Esther and today I'll be presenting on prompts. So to start off, let's see what are some of the possible ways to allow for high model performance. First, we should train the model with as many data as possible. The more data points to learn allows for the model to understand the dataset better and hence perform better on a specific task. Next, we should also use big models with large number of parameters. Okay, so say you have loads of data and have a gigantic model to train. Does that mean that the problem is solved? As you can see here, a T5 small models with 60 million parameters trained on 1 trillion trading tokens takes 2 days. But for the GPT-3 models with 175 billion parameters, for 300 billion tokens, it takes approximately 3,640 days. That is a lot of days to train and very painful to see when looking at the electricity bills. Therefore, for NLP, researchers have proposed using prompting to tackle this problem. So to start off, what exactly are prompts? And what better way to ask this question than to ask the ChatGPT? To summarize what has been mentioned by ChatGPT, prompts are input statements or instructions that users provide to guide the behavior of a language model, such as the ever-popular ChatGPT. Here, the prompt is the question, what are prompts? So what is the significance of prompting? Prompting is able to aid large language models to perform zero-shot tasks, such as summarizing, inferencing, which are the classification tasks and the natural language inference tasks, transforming, which are the translation and spelling correction tasks, and finally, the expanding, which are the ones that can generate essays based on a prompt. So to show you an example, here's a question that I asked to ChatGPT. The prompt here is to ask the model to classify between positive, negative, and neutral stance towards the topic climate change. Then we can see that the ChatGPT replies and says that the stance is negative with an explanation. The reason why prompting is so popular is because prompting is very similar to having a conversation with a human, whereby we provide a context and ask them questions. So prompting allows for no training of the large language models. By giving a piece of text and asking a natural language question, such as the one shown here, we are able to obtain an answer. This means that we are able to save time on fine-tuning the models. With the right phrasing of prompts to the model, it can definitely improve the accuracy and quality of the answer by large language models. However, if the user would like it to work on one specific task, for example, stance classification, it would still be better to fine-tune them on that specific task to ensure greater accuracy. Now, if we do not plan to fine-tune the models, how can we then ensure that the model is able to consistently do tasks with high accuracy? This means that we have to actually improve on the prompt. So what we can do here is to perform prompt engineering or prompt tuning. So let's go through them one by one. For prompt engineering, it is when we manually design prompts to prompt the large language models to give a specific output. There are a few types of prompt engineering. First, it is the zero-shot prompting. Zero-shot prompting is whereby we do not give them any examples and directly have them solve a question. Of course, with zero-shot prompting, we don't get to tell the model what kind of output we are looking for, or it also could be because of the fact that the model did not perform very well. In this case, we can do few-shot prompting instead, which is to provide at least one example in the prompt to further guide the model. Another way to teach the model is to perform chain of thought prompting. Chain of thought prompting involves reasoning in a step-by-step manner, which allows for the large language models to also perform logical reasoning, which is especially effective in math problems. Hence, with these approaches, it signifies that the models do not need to be fine-tuned at all, and this saves a lot of computational time. However, there are some limitations of prompt engineering. First, we need to understand the large language models well enough to know what kind of prompts the model responds well to. Next, the phrasing of prompts can affect the scoring as well. For example, using the BERT model, changing the prompt slightly, such as adding 1 or 2 more words, can drastically increase or decrease the precision at one scoring. Taking a closer look at this table, from the original prompt that did not ask any question, for example, if we added additional words such as or state, it actually decreased the precision scoring. However, asking the same question without the or state and adding in one additional word in y, this y is the target, it actually increases the precision scoring instead. So to tackle the limitations of prompt engineering, we can consider prompt tuning. Prompt tuning uses a trainable model to output embeddings into the large language models. So how can they generate prompts? Because it is self-prompting, this means that the template will be created by a model. This paper called GPT Understands 2 has proposed p-tuning. For p-tuning, they explain that the function of a prompt is to organize context, target, and itself into a template. For example, in the task of predicting a Britain's capital, a template may be the capital of Britain is blank, and this blank is replaced by the mass tag. So over here, Britain is the context, the mass tag is the target, and the remaining words, the capital of, that is actually the generated prompt. So the p-tuning idea shows that prompts can be so flexible that we may even insert them into the context or target. In addition, adding more task-related tokens, such as capital, as shown over here in a red circle, into the prompt will bring further improvement. However, this p-tuning model leads to 2 limitations. First, the number of tunable parameters is limited due to the constraints of sequence length. Secondly, the input embeddings have a relatively indirect impact on model predictions. As you can see on the figure on the right, the p-tuning model, the embeddings are only found on the top layer. So to address these challenges, p-tuning v2 is proposed, as shown on the right. This model employs the idea of deep prompt tuning. As illustrated on the figure on the right, prompts in the different layers are added as the prefix tokens. This is the main difference as compared to the figure on the left, whereby the orange embeddings are on the top layer only, while the orange embeddings in p-tuning v2 are found on every layer of the model. This allows for the p-tuning v2 model to have more tunable task-specific parameters to allow more per task capacity while being parameter efficient. In addition, prompts added to the deeper layers allow for more direct impact on model predictions. So here are the results. FT over here is the fine-tuned models, P is the original version of the p-tuning, and PT2 is the second version of the p-tuning model. So as you can see for PT2, the results are actually pretty much comparable to the fine-tuned models. This shows hope that we do not need to fine-tune models that take up a large amount of time to compute, and rather we can just rather train a smaller model to generate prompts from large language models instead. However, there are definitely some drawbacks to adopting the prompt tuning approach. One very significant limitation is that there is the lack of interpretability. The prompts are generated by models into the embeddings in a continuous token space instead of discrete token space like the hard prompts created during prompt engineering. As a result, if you would like to understand what is the output, which are in terms of embeddings, we need to perform additional steps such as performing k-nearest neighbors to get a general idea on what topic that they are referring to. So with that, I will end my section of the whole presentation. Thank you for your kind attention. If you are interested in prompt engineering, here's a course that you can check out.
Okay, let's thank Esther for her presentation. So our support team, if you have prepared any questions or discussion, we can have them now. Anyone from our support team for week 3 have anything that they want to inject?
Yeah, that's also for those on Zoom, right? So, and also for those here. So like Esther's not here today, so we put the Q&A session for hers and Richmond's, right, inside the scribe notes. So you can, if you have any questions, right, she'll answer by the end of the day. So just write your questions in the document, then she'll answer them. So now we move on to like in context learning, which is presented by Victor. Is Victor here?
Yeah.
Oh, you want to come here because they can raise the slides.
Yeah, I want to say a couple of things before Victor starts. So we talked about prompt tuning and soft prompts. Does everyone understand what's the difference between a soft prompt and a normal prompt? Can anyone tell me what it is? Go ahead.
Normal prompt is
Okay, so if I heard correctly, a normal prompt is just one that you stick into the model directly by typing it in or using a API to enter. It's in natural language tag, so it's discrete. Okay, because you take those words and then it gets fed as embeddings into the model to interpret state, right? So the prompt, the actual words get converted into a continuous form through the embedding model, right? Okay, and our soft prompt is not like that, right? It's just a continuous vector, just like after we have it in embedding form. And because we have it in embedding form, it's just a vector, so it's easy to tune. Are there any other parts that we want to take note of? Anyone else want to clarify more deeply on this?
Yeah, I'm just curious. Why
Yeah.
do we always say zero-shot models? Because aren't most LLM models very useful?
Why? So the question is, why do we call LLM models zero shot?
Yeah, why do we like prefix it? Like it's already understood that zero-shot.
It's already understood that it's zero shot. So yeah, I agree with you that when we normally give a task to an LLM by a prompt, it's generally zero shot because you're not doing any demonstration, right? So I guess the technical community wants to distinguish whether how many trials the system has had with it, and to distinguish cases where the LLM is frozen, meaning the parameters are not being adjusted, versus when it's tunable, right? When you see the fire icon, right? So when the LLM is parameters are being tuned. So when it's frozen and we give some demonstrations, then we call it end shot, right? But you can also do this not necessarily as a frozen, right? You can give end shot or a few shot fine tuning as well, right? So everyone knows the difference between fine tuning, right? Fine tuning means that we allow the LLM's parameters or parts of it, like if you have an adapter, for example, that we talked about last week, to unfreeze those parts of the parameters and have them tuned by gradient descent and back propagation, right? The round trip. Okay, everyone clear about that? Okay, great questions. Thanks for asking them. Your name again? Vincent. Winston. Okay, thanks, Winston. Okay, so Victor, you can take the floor. Thank you.
Okay, yeah. So after the just now the talk about the prompt, so I will go on a further step talk about the in-context learning. According to my understanding, in-context learning is just another format of prompt. Yeah. So the traditional prompt, we say, let's take the task of sentiment analysis as an example, right? So the the prompt we talked just now, right? It's just a prefix of the context that can get the model through a certain task, right? You can change into any format as long as it fits your training data. So here I just say the prompt is called sentiment. So the very traditional setting is we use the prompt plus the context, and we directly input to the model to ask for the output. This is a very typical setting of the prompt. But later on, as the evolution goes on, right, we change the prompt into a instruction format. The instruction format is written in natural language, which allows the language model to learn the certain description about the new task. So, for example, for the sentiment analysis task, you can convert it to an instruction like, can you identify the sentiment in the following reviews and classify them into positive, negative, or neutral? So this is a very clear instruction, and to the language model where you can perform the instruction prompting. And moving on, right, the topic I'm talking about today is called ICL, which is in-context learning, right? The difference between in-context learning and the instruction is that besides the instruction, we also add on few of the examples. So after the instruction, you can see that we can add on example of review 1, review 2, and review 3, and we gave the label of each of the reviews. So this is a process called demonstration. So by giving this demonstration, we ask the model to return the value of our testing input, which is the review of good meal. We want the model to predict whether it's positive, negative, or neutral. So it's another format of prompting. Okay, so as the example shows just now, right? So we gave a formal definition of what's in-context learning. So in-context learning is a paradigm that allows the language model to learn tasks given only a few examples in the form of demonstration. So as I talked about now, the demonstration is composed of an instruction and a few examples. So together is called demonstration. So using ICL has a few advantages. So the first one is that the demonstration is written in natural language. So it provides an interpretable way that you can communicate with the large language model. You can do it either by the web interface or through the API of the language model. It's very easy, right? And the second thing is that the ICL learning is very similar to the decision process of human beings by learning from analogy. So this is quite similar to when you prepare for the exam, right? You learn the instructions, you also read past year papers that serve as an example, as also as a demonstration. So you use that one as the demonstration, and you can better prepare for the real testing in the real exams, okay? And the third advantage is that compared with supervised training, ICL is a training-free learning framework. But here I want to mention a point that training-free doesn't equal data-free. So you still require some of data as example so that you can perform ICL. But here I want to ask a question. So do you think ICL is a zero-shot or few-shot learning process? Okay, yeah, I know most of you must say it's few-shot because you provide examples to this model, right? But I have a question here. So let's suppose all the labels I provided are wrong. So I just randomly provide labels to the model. So do you consider as zero-shot or few-shot? So it means like for the same examples, I just randomly assign any labels to the model, and I use this one serve as my ICL prompting. So is that zero-shot or few-shot? Okay, yeah, we can leave this question to next presenter, or you can answer after my presentation. Okay, so this is a question. We can think about it later, right? Okay. Yeah. So for the same, let's talk about the general formulation of ICL, right? So given this example, we can see that the ICL actually it takes the query input text X and the set of candidate answer Y. So that is the and also a demonstration C. As I said before, the demonstration must include an instruction and few examples together. So by taking all this input, ICL actually the large language model will generate a likelihood of candidate answer by a certain scoring function, and the ICL will certainly output the prediction with the higher score. So this is typical decision process from the language models. And I was referring to a very good survey, I think, about the ICL. So in this survey, he adopted such kind of taxonomy. So he talked about the ICL with training and inference. So many of us think ICL is a training-free process. Why we still need training? So here the author gives the answer. We don't really train the model. Actually, we just do a warm-up. The warm-up is to better prepare the model for the format of the demonstration so that it can perform better. So it's a slightly fine-tuning, but not really the pre-training. And we also focus on the inference where we don't do the training. We already inherit the model for the inference. So I will talk about both. And for the warm-up, I will talk about the supervised model. And for the demonstration, I will talk about what are the key factors that affect the final performance in demonstration. But the scoring function, we will leave it for the future, okay? Yeah, so the warm-up, the main purpose is to adjust and prepare language model for ICL and bridge the gap between pre-training and downstream ICL tasks. Okay, so it's generally adopted in the several formats and several methods. So for example, you can continue training the language model on different tasks with the demonstration. So the demonstration will match the format in ICL. Or you can also continue training the model on different instructions. So the instructions should also be matching the ICL prompts. And another different way is called symbol tuning. Symbol tuning is to fine-tune the language model on in-context input pairs, but we are substituting the natural language labels into arbitrary symbols. Okay, so for example, here I show an example. So the symbol tuning. This one, okay. Yeah. So the symbol tuning, okay. So the previous natural labels are positive, negative, and neutral. Yeah. So we are substituting those labels into a symbol like for or bar. So, and we will do a fine tuning based on the symbols. So this is a way, right, to force the language model to learn from our examples because we change the way of the labels, right? So the model cannot rely on the previous knowledge of the relevant labels. They must learn from our examples. So this is a it's a way to force the language model to do ICL. So it's all these three ways together is warm-up process. Okay, and besides the training, we can also say that most of us just perform ICL with inference. So what are the key factors that affect the ICL performance when you are doing the inference? So I'm summarizing them into these four aspects, which are the example selection, ordering, the instruction format, and reasoning steps. So the most key factor is the example selection. So how you select the example, does it matter to the final performance? And the answer is yes. Yeah, it really matters. But so most of the research has proved that if you are selecting the semantically close neighbors of the testing samples, it will help improve the ICL performance. So you can select by the certain matrix like a predefined matrix like L2 or cosine. But what I say is about the input of the testing samples, means the context, instead of the labels. We have also research proved that the labels doesn't matter so much for the final ICL performance. That's why I say just now, you randomly assign labels, if your performance will drop slightly, but it's not so much compared with you assign the ground truth labels. So this is an interesting topic. I cannot answer is the ICL is still short or few short because you can also assign random labels to the ICL prompting. And we don't have a certain reason to explain why it happens, but maybe if you want to have a discussion, we can also have a discussion of this one, why the labels doesn't matter so much in ICL.
That's
Okay.
a great point to stop. So why do you think the ICL labels don't matter as much as, for example, the training data? You know, the example demonstrations.
I can give a
Please go ahead.
hypothesis.
Yeah.
Yeah. I think like a lot of the tasks you see require maybe some bit of like symbolic logic, and when you replace the labels, the symbolic logic is still intact, and that's what you want to train in the neural network. That's my guess. Yeah. Or in another sense, it's like some sort of composability, I guess.
Okay. What do you guys think? I think that's a good start, right? Like many times we want our distribution of our test samples to look like our training data. right? So it's important that our training data that we give through demonstrations looks like the test, right? In some cases, our test is I'm sorry, I forgot your name.
Oh, Nicholas.
Nicholas said is that you have a long chain of reasoning or you have a complex task, right? So that depends more on the demonstrations than the final label, right? So if you have a complex task, maybe the demonstration matters more than the label, right? But if you can say, okay, the task is actually very simple, the labels play a large part in that, maybe then the labels may play more of a role. So we can try to demonstrate that. That would be interesting to look at to say, okay, I give it a simple task. Okay, then I'm giving very simple addition questions. There's no multi-step. Okay, 2 + 2, 5 + 8 or something. And if the labels are wrong, well, then maybe you won't learn as well, right? But if it requires a lot of chain of reasoning and I demonstrate the chain of reasoning from chain of thought, then perhaps that demonstration is more important, right? So I'd like you guys to think about it because a lot of times we see all these things like, oh, you do ICL or zero shot. We haven't really thought deep enough about why does the language model, how is it able to do all these things, right? How can it reason through its prediction of masked words that it can accomplish these tasks in the first place, right?
Yeah, okay, so I continue, right? So the another factor that applies ICL and is very related to our experiment is that the ordering of the examples. So let's suppose we have K examples, so you can arrange like factorial K ways to arrange all those examples, right? And the order does matter. So the experiment has shown that the default order, which put the most similar ones in front, is better than the reverse way how you organize all the examples. But there's no research showing that the numbers of example is matters. So I hope any of you can conduct experiment to test that. So for example, if you we have only one example compared with the results when we have multiple examples for ICL. Does that matters? Yeah, and this is an open question for all of you. Okay. So for the instruction format and reasoning step, I think I will not talk about them. Later you will hear the presentation about chain of thought. I think it will answer some of your questions.
Okay, for ordering examples, I would like you to think also about the state space of how we are drawing the decision boundaries about what words to predict, right? So at every point, when you get a new word to predict for the LLM, how does it decide which word to generate, right? So when you are demonstrating or creating samples or examples that are sequenced differently, near the center of the distribution or far away, an outlier, how does that influence the decision boundary? Okay, and then how does that affect the performance? So for example, if you give an outlier label, that's going to shift the decision boundary a lot. Right, and it's also going to instigate more variability, like the variance on responses should be higher if you give an outlier as an example, right? So in the case of zero shot, right, you don't have a lot to go on. If you give something that's an outlier, you're making it very variable, right? Because you only give one shot demonstration, right? So it makes sense that if you order it with things closer to the centroid of your expectations, that you would get better results. You guys understand what I'm saying? Okay, so I want you to think about it from that point of view, from a distributional point of view, about where the samples lie in space. Why would it make a difference that the ordering matters? And how would you approach it in your task? Okay.
Okay.
Yeah, go ahead, please.
Would you like to both label or answer into the qualifications? So what would happen if the large language models were always like 100% right? Because you can the labels as one of the qualifications.
If you give the label in the few shot case to be right or wrong, sorry, right.
The labels or the correct answers in the future. Then will the large language models always like 100% values?
So I think that's the case that if we give demonstrations that are always right with all the right labels, it's not necessarily guaranteeing anything, right?
Yeah. It's this if you have all those correct labels in your ICL prompting, compared with your randomly assigned labels to ICL prompting, your performance will be slightly better, but it doesn't worse the time to do the labeling.
No, I mean, you put the correct answer as one of the examples to provide to the large language model.
Yes.
I mean, if you ask a question and you already provide the correct answers for the models, will the model be like 100%? Get the 100% accuracy?
You mean for the same question? For the same question you're showing an example, I guess so. But
Okay, so who says yes? You'll always come back. Okay.
So I already tested this several times. It really depends. It really depends. So you know the large language model actually means all the distinct model. So there is no ensure that you give the same question in the demonstrations. The model will answer exactly the same as the answer you provided in the form. So there is no ensure.
There's no
And
guarantee.
I already tested many times already. So it really depends. For example, you can test some long answer questions. Then you will find a lot of times the model generates the answer maybe different or very different from the demonstration. I mean, as you demonstrate, slides like use a game to find the most similar examples compared to the test data. And I think the boundaries like the very same examples as your questions.
Okay, so you are saying that you provide exactly the same question, so is that's the closest neighbor of the testing samples, right? And you are asking about what the performance of this way, right? Okay, I don't think the research was done considering your case, right? When they are comparing the nearest neighbor, they shouldn't consider the case of exact matching. That's my concern about this one, firstly. And secondly, as we have already have the experience, right? We don't know whether you're repeating the same answer from the given example, or you will just, as Nicholas said, right? They will just learn the certain concept and try to provide their own solution for the question. So that's something that I cannot answer right now. Yeah, but
Actually, I suddenly recall something that we provide a bit more information. Like, okay, even if you give the exact answer inside the prompt, I guess experimentally, a very long time ago, there was this thing called ResNet. And what ResNet shows is that using a neural network to model the identity mapping, just copy the input and output, just to copy, is really a struggle. And that's why you have that skip connections that literally just add the identity. So this may give us some intuition that like neural networks in general, like, yeah, even the identity mapping is a bit so. And then now back to this example of maybe it's some form of partial select, like for give a few examples, one of them is the exact answer. It has to select it and then perform the identity mapping on that. And you can sort of like, I guess intuitively guess that there's still some like error or difficulty, I think. Yeah.
Okay, this is a good discussion.
Are we making assumptions that the settings like temperatures, all that is default? What we did was we had the same issue as well, like trying to get the same answer back. Providing same labels. We found that adjusting temperature lower does help, but it gets to a point when it gets too low, it is not creative anymore. It tends to be like, robotic. So you get all the same responses, but then it doesn't perform other good inferences at all. It's just a Q&A bot. That's it, right?
I want to add on. So if you really want to get exactly the same answer, so one trick is that you repeat that demonstration. The other forms.
Also can.
Yeah. So I already did that kind of trick. So you repeat that question again multiple times in the form. So in that, by that way, you try to emphasize the model, right? The one multiple times. So then it really helps.
Okay, we have another comment here.
Actually, I have a project where we dropped the temperature right to 0 for like OpenAI,
Right.
and it still gave random results. And in fact, OpenAI, like I think there's a note there that says, even at temperature 0, don't expect deterministic results.
Still gonna play with the K and P. But even then, it's
I think like even there was one note by DAI, the deep learning AI. They say don't change if you put temperature 0, don't play with the other.
That's crazy.
There is actually no deterministic, right?
Yeah.
Temperature 0, it means that you don't try to make the distribution
Right.
smooth. You don't. So yeah, so it is still a distribution.
Yeah.
Yeah.
There's no
That's the
guarantee.
point. Yeah.
No guarantee.
Yeah. Still.
I think, okay, I'll try to explain my concept. Okay, so like if you drop the temperature to 0, you just like, okay, let's say you write down like a softmax function or something. So what it does is the top, the highest scoring one is pushed up all the way to the maximum score, whereas the non-maximum is all pushed to 0. Maybe later I'll just write something like that to show that. But the thing is, okay, it may still be probabilistic if, let's say, there are two equally scoring ones. Like for example, there are two answers, like two tokens. Each of them has like 30%, 20%, and then the rest of them are like less than 30%. Then when changing the temperature to 0, these two 30% ones will shoot up to 50-50, and the rest will be 0. So there's still like a 50-50 chance. So there's some probabilistic. But the thing is, I get where that like suspicion comes from about why is it that temperature 0 is not deterministic. It's because like in the formula to achieve a distribution, all of them must be exactly the same score, which in the space of like when you play around the softmax and stuff, like it's just not likely, right? They can have the exact same score, like a bunch of the exact same score, and therefore have a distribution that's like equal with the
Okay. So even if the same distribution, you still not sure that the output will be the same, because the point is the decoding strategy. That's the point. So you might already know decoding, they do not perform the sum on the whole dictionary, not on the whole dictionary, but instead picking a random a sample. So that's the point. That's the point. Even if you got the same distribution, you are still not very sure the output will be the same because of the decoding strategy.
You know what I'm trying to say is my assumption is that in the decoding strategy, the temperature that you apply is affects that decoding part. And is it still
picking sample to generate?
So I'm saying that when you're at the last stage, you're picking from a distribution. But when you change the temperature, at least if you use the softmax function to normalize it, I will write down the method that if you change the temperature to 0, it will boost the probability of the highest scoring one to all the way to the highest, and all the other non-highest ones will be suppressed to 0.
I think I have like an additional comment. Like it also depends on the implementation. So like for your case, right, that's like for the probabilistic case, I feel that that's more of like when you have a multi-normal distribution from the temperature. So some people, what they do, right, in some GitHub repos, they actually just use argmax instead of sampling from a multi-normal distribution. So in that case, right, I feel it'll be deterministic because if you just use argmax, right, you're always taking the highest probability in that case. So, and for PyTorch argmax, I'm not so sure, you can correct me on this, but I think it just takes the first highest probability. So if there's multiple with the same score, right, you just take the first one for PyTorch. So if you use the argmax for that, right, what happens is that you just take the first highest scoring one, and in that case, that'll be deterministic. But then if you sample from multi-mode distribution, which is like what most of the papers in usually practice, right? Then of course it'll be probabilistic, because there's still sampling of distribution in that case. So that's my thoughts.
Okay, I think you'll explain it. I'll
Yeah,
explain
sure.
it and then
Okay.
You have the same distribution and you use a deterministic decoding algorithm. Then in that case, you can expect that the output is the same. Otherwise, you cannot expect the output the same.
Okay, I think we will discuss this later.
Okay. So I will discuss the temperature later. Okay, yeah. So I will continue, right? The last part. Why ICL can't work. This is a very big topic. I think we definitely cannot answer it today, but just give you some idea about like some existing explanations. Okay. So the first thing is the distribution of training data. So they are saying that ICL as an implicit Bayesian inference is ability to emerge when the pre-training distribution follows a mixture of hidden Markov models. How to understand this one is that very similar to the concept mentioned by Nicholas just now, right? So they are saying that actually the ICL is a process for the model to understand certain concept. So if the model can infer this concept from the existing prompt, then it can better infer the output from both the concept and the prompt. So they convert it to such a posterior Bayesian probability distribution. So they're saying that the model need to first infer the concept from the examples, and then they're trying to infer the output. So this is one of the explanation that I think is generally accepted, right? And another explanation is that the learning mechanism of transformer. So they are saying that transformer can encode the learning algorithm to learn some unseen linear functions. And the transformer can also have the capability to learn the gradient descent during the inference time. So for example, they're saying that the GPT can produce a meta gradient according to the demonstration examples. And this meta gradient will be applied to the original GPT to build the final output. And they build up the experiment to observe that actually the changing in the attention weight is in the same direction when you are fine-tuning the GPT with gradient descent approach. This is another explanation. And the third explanation is that the functional components. They're saying that there exists some induction head in transformer that will copy the previous pattern to complete the next token. So how to understand this? In other words, it's saying that the transformer has the capability to pick up the keywords. Those keywords are determinantial to the final outcome. So for example, I show an example here. So this is the experiment. They check for the information flow from the keywords to other words. So when it's in the shallow layer, means in the very beginning layer, right? They find out the connection is not so obvious. But with the layer goes deeper, they will find that actually there's a more strong information flow from those label words to the potential outputs. For example, the label words is sentiment, and the output is negative or positive. They find more strong connection with more deeper layer. And when they are trying to block those label words in the shallow layer, they will find that actually the information flow in the deep layer just disappeared. This is another way to explain why ICL works. So I just summarized three of the explanation, and you can go in detail if you want. So as the conclusion, I think ICL has demonstrated its efficiency in many NLP tasks through a training-free process. And the existing research mainly focusing on warm-up sightings or a special demonstration format sightings. And knowing or considering how ICL works will definitely help us understand these mechanisms, okay? And future research can also extend ICL into different modalities, for example, visual and multi-modal sightings. And that concludes my presentation. Thank you.
Any questions for Victor about ICL? Anyone on Zoom also can also ask questions. Not really on Zoom for now. Anyone here got any questions about ICL? If not, then we move on to the next presenter. So the next presenter will be Richmond, who's not here today. Yeah, Richmond will not be here today, so we will use his recording instead.
We have recently on zero shot, one shot classification. So the first up is zero shot bonding. What exactly it is actually using pre-given visualized materials samples. And the main idea of zero shot bonding is actually to make electrons the way we understand takes a lot of us. And one is that
Premix. Oh shoot. How do you it's kind of soft. Is there any way you can simplify it?
Maybe change the output to the two speakers here because it should be connected, right?
Okay, let's do that. How do you do that?
You on the Mac, it's there's a sound icon on the top right.
Yeah, actually help us the sound.
Yeah, we can help it.
Which one is it, the Yeti or the Sunflower?
External HDMI.
Okay, sure.
Oh yeah, like workers projector.
Yeah, let me try. Let me see whether it's better. Is it better?
Yeah.
Or you?
Only for even here you got to post it up.
Yeah.
With the audience, probably the Zoom audience will be have the
Yeah.
same problem.
What is Sunflower? Is it the TVs? That doesn't do anything. Shoot. Yeah.
Here to adjust the voice on the YouTube.
Try already. Yeah.
Yeah, it's max really. We got the extra HDMI that works.
Yeah, the extra there should be some remote or something. Is there a console thing?
Let's see. You can play the device.
I don't think anyone can see the console for the extra. Okay, I see something here, but I don't know whether you can boost the volume from this thing.
I don't think it should be such kind of thing.
Yeah.
Let's try it from my tablet.
So on those on Zoom, you just wait for a while because you're trying to boost the volume for the video. Is it that one?
Press access.
Oh gosh. I don't know, the message drops. Because I don't know.
Maybe the next presentation come back when Prof is back.
Sure, maybe do that. So for I think we'll skip.
Should be here.
Oh, this one. So this one. Source volume go up. Oh, yeah. Okay, let's try this.
Try.
There
you go.
Yeah. All right.
we have recently on zero shot, one shot, so
Yeah, it works.
so this up is zero shot bonding. What exactly
Give it a while because it's
is actually using pre-given model visualized materials as an example. And the idea of zero shot bonding is actually to make electrons and the human the way we understand things around us and find similarity in data classes. It learns intermediate symmetric layers and properties to predict class of currency data. So in short, zero bonding is training with a set of data and using the pre-trained model to predict on top of unseen trained data. And maybe more visual understanding of zero shot bonding, on the left side, in the form of imagery. So the C classes are the multiple linears. We found it in model. And we also included in semantic attributes such as long face, Atlantic, short, and etc. So we use knowledge transfer and of the model to actually infer based on C class, which is the zebra picture. And based on the semantic attributes of the zebra, the model can actually predict that this picture is referring to the zebra. And in the context of natural language processing on the right side, I actually use ChatGPT to answer a few questions with zero shot bonding. So I asked it to write an introduction of that post, and it performed pretty well. This would be rather like the more elaborate introduction of the code, and this is the zero shot points. So how does the zero shot bonding, or how does the model actually understand based on just zero shot bonding? So these are the various points that the model actually understands and does its inference. So for statistical learning, during pre-training, the model actually learns the statistical relationship between words and phrases in the text data, and it forms associations between words, understanding context, and will probably segment the model. For example, it learns that water is wet is a more common phrase than water is dry, and it assigns higher probabilities to the former. For contextual understanding, the model excels at understanding context. It doesn't just rely on base rules or templates, but adapts its responses based on the input it receives. User contextual information for the surrounding text, determine the most likely interpretation of query. For pattern recognition, the model is actually good at recognizing pattern, or we use it and pattern. It can identify relationships between entities, rely reduction, and draw common sense knowledge. For example, it knows that birds can fly, and asks, can penguins fly? Can infer that penguins are a type of bird, and respond correctly, no, penguins can't fly. And for probabilistic reasoning, large language models operate on probabilities, and when faced with multiple potential interpretations or responses, they choose the most likely one based on patterns and data. And this probabilistic reasoning allows the model to handle uncertainty and make educated guesses when faced with ambiguous queries. And lastly, the transfer learning, the model's ability to make inferences about unknown data is transferred. Leverages the knowledge gained during pre-training and applies it to new unseen tasks or problems. The model can generalize from its training data to understand and respond to a variety of queries, even though CSRs specifically encountered. And these are some of the examples of social prompting. Can be deployed on tasks where you don't really need specific domain knowledge, such as text generation, as well as general question answers. And based on the example that I showed previously, we check the images to show an introduction of, or to give an introduction of the level, and it's able to perform the task very well because the question that the prompt asked is not generated. However, the limitation of zero-shot prompting is that the quality of the response varies according to the complexity of the task, and it relies very heavily on the quality of the pre-trained model. So if your pre-trained model doesn't, one pre-trained model is like maybe 178 parameters, similar to one that's 68 parameters. The one with lesser parameters are likely to perform much worse with zero-shot prompting as compared to one that's higher parameters. And it's because of the vast amount of information and knowledge that the larger language model has. And it is also not very good because it requires in-depth domain knowledge. If you're asking very specific in depth, let's say in the field of healthcare, the model might not be able to explain up to the detail and the depth that you want. And next, we have one-shot prompting. Similarly to zero-shot, I said perfect that it requires one instances of each class to predict unknown data. So each shot is to make more context and more knowledge for the model to make a more accurate prediction. It's actually to improve the result by providing much more information. So similarly on that, it's about understanding of one-shot prompting. The query is a picture of a squirrel, and without knowing that it's a squirrel, and the model has a picture of every animal classes that forms very easy classifier. And when we ask what is this animal based on particular given, the model will understand that we also give a probability of 0.9 to the squirrel, and you understand that okay, this image is referring to the squirrel. And in the context of natural language processing, the website, ChatGPT can actually answer the question for short prompting by giving it a format that I want to reply. In form of quick set, characteristic, whether they eat, so as to identify the status. And the same example and same context of writing introduction to variables. Instead of asking it just on variables, I want to write introduction to crocodiles in the above structure. And as you can see, the bottom response is like basically is called to the B. So the application for one-shot prompting is actually for question answer or domain knowledge and a question more specific content like and as well as code generation. You can provide it in the format that you want code to be, the languages that you want, Java, and etc. You can answer your query according to the format that you specify. Other limitations is that it is limited guidance or features are inadequate when you use tasks. So for limited guidance, what it means is one-shot prompting provides only a single example for him to guide the model, and this can be insufficient for complex tasks that requires a broader understanding of the task or context. And the model may struggle to generalize beyond the provided example. And for overfitting, when the model has access to just one example, it may only rely on an example and produce results that are too similar to it. This can result in responses that lack diversity and feel attracted to solve the task. And for inadequacy, one-shot prompting is less effective for tasks with ambiguous or multiple valid interpretations. And the model may not have enough context to disambiguate and provide the correct responses. Lastly, on few-shot prompting, it refers actually to building a model with more data, but more than zero-shot prompting or one-shot prompting, and it is related to the task that you want to understand. It generalizes well on unseen data with very few examples of connection. Similarly, that side, suppose that instead of one picture per class, maybe two, or maybe if you want one. And in this context, we have an armadillo, so temporary images. And our query is whether or not this animal is armadillo or temporary. And model will have predicted that it is temporary. And in the context of natural language processing, where I'm using ChatGPT again, to answer same question, but this time instead of one shot or zero shot, I'm giving it a few shot for an introduction on dolphins, provided with the context of the animal without stress and the format that I want. As you can see, in response to the bottom, we provide exactly what I want it to provide and provide some context information about dolphins in the same way that I can for the few examples that given. And for the application, sentiment analysis, because as we give different examples of whether or not we label is progress. The order this response is positive or negative, you will learn based on context and few prompts that we've given to much accurately predict subsequent or unseen sentiments. And with regards to customized language translation, if you're just doing pure rather general language translation without a specific format, zero-shot prompting will work. However, if you want more customized one, then you want it to translate in a certain way, skip a few words, etc., then that is how that is the case that you will use zero-shot prompting. And for question answering with in-depth domain knowledge, like what examples that I provided previously, which is on the language without response, you'll be better to explain that in the context of anything. The limitations for zero-shot prompting is actually data dependency in machine because finding complexity. So for data dependency, zero-shot prompting relies on a small set of examples of games. If the provided examples are not representative or do not cover the entire task space, the model's performance may still be disappointing. The population methods, as increase the number of examples in zero-shot prompting, there may be diminishing returns in terms of performance improvement. Adding more examples may not necessarily give proportionally better results, and it can be computationally expensive. And for fine-tuning complexity, fine-tuning a model with few-shot form typically requires additional steps and resources, including capital selection and pre-processing. And for some examples, giving few-shot prompting might not actually improve the accuracy of the result. and you actually need a hyperparameter tuning and task-specific data to actually improve it, and involve more than 0 shot, 1 shot, or even 3 shot content. So what are the differences between different functions? So in short, 0, no example, 1 example, 3 shots, no example. So in terms of the definitions, they differ in terms of the different examples. But for the applications, what we know is that the 0 shot is more for general knowledge and tasks that are more generic, where you don't really need responses for specific domain knowledge. And of course, it's used for language translation. So if you have knowledge queries, for 1 shot, it's for minimum task specific data, but if you want a better performance, then a 0 shot. That's where you use it for machine service as code generation, and of course for 2 shot, more data, so it's 1 shot, but also more to be able to fine-tune the model response. And this is usually used on top of foundation model where you have to just fine-tune the model based on. And that's what we usually call prompt engineering. And we'll also use it for customer translation for content generation as explained earlier. So this is just a very rough picture of the differences between 3 of them, and the list of the applications are exhaustive. And based on research paper that we've shared I think over the weekends, on language models of visual system. So this particular report has shown that for 0 shot, 1 shot, so as 3 shot, the effectiveness of increasing the accuracy varies according to how large the language model actually is. So it's considered for 1.3B as well as 30B, that considers a small similar to 150. And for 0, 1 shot, or 3 shot, the accuracy doesn't differ too much. However, for a very huge model, the accuracy between 0 shot, 1 shot, 3 shot actually is a very huge difference. And if you want to improve the accuracy of the model, one thing that we consider is also how many parameters is being used and whether or not should we format using or should we do function to. That's all for my question. Thank you.
So, do you have any questions for like few shot and 0 shot prompting? The Zoom also you can ask. Apologize for like the voice quality because I've tried to put through a denoiser. Yeah.
You need normalizer.
Yeah, I need a normalizer. What with it?
Speech.
Yeah.
Nice.
Okay. So if no one has any questions on Zoom or here, then I will move over to Suveen. Yeah, to present on chain of thought. Slideshow.
Hi everyone, I'm Suveen and I'll be going through chain of thought. So before going like explaining chain of thought, I'll explain what reasoning is. So as we all know, like if you have taken a math course recently, or like if you have like tried asking ChatGPT any math task, ChatGPT doesn't perform that well. And like to summarize reasoning has like 3 main categories: arithmetic reasoning, which involves math, then symbolic reasoning, it's questions like last letter concatenation, and coin flips. So coin flips, it's a very common thing that people test large language models on. So it's like you say the initial state of a coin is heads up, then I flip it, then someone else flips it, then again someone else flips it, and we ask the model what's the current state. And then we have common sense reasoning, which involves common sense. We know that like ChatGPT, it's like it has this inability to reason, and so this is from one of my modules. This same, it's about discrete mathematics. So the professor, he wants us to get ChatGPT to prove logics and try to find try to get ChatGPT to admit that it made a mistake. So we have to repeat the steps until it apologizes. So I found it's really funny. Yeah. Then so to overcome those reasoning issues large language models have, we can have little prompt improvements, but it's a hassle. So for example, in this question, we try to reverse the letters in the word lollipop, but it gives a wrong answer. But by adding dashes between the letters, you can easily get the correct answer. So yeah, this is mainly because of the way it tokenizes the characters. But yeah, it's a hassle when you try to do things in a large scale. So researchers have been trying to tackle this problem of getting language models to reason. So they tried scaling up language model sizes. And if you see the PaLM 540 billion parameter model, it only has 18% solve rate in this mathematic question data set. So yeah. Then they also like in 2020, this paper, Leap of Thought, what they tried was they tried to fine tune. They try to produce a thought process via fine tuning. So the idea is if you give explicit rules and some implicit knowledge, you can get the model to reason and get the answer. So the example taken here is that you give the explicit rule that a mammal has a belly button, and the implicit knowledge that a whale is a mammal, and it is able to understand, okay, since whale is a mammal, it should have a belly button. The thing with this model is that you beforehand you can know the performance of the module. So if you fed the data in, it gives the correct answer. If the data is not there, it does not give the correct answer. Yeah. So this is a paper that introduced chain of thought prompting. To give it a definition, chain of thought is a series of intermediate natural language reasoning steps, which will lead us to the final answer. Yeah. So here we have a comparison between standard prompting and chain of thought prompting. In standard prompting, what we do is we give a question and we give the answer, and we ask another question which is not similar, or like we could be similar as well, and it gives the wrong answer. But here in chain of thought prompting, what we do is we try to go step by step. We say, okay, we start with this step and we do the other things, and this is how I got to the answer. And the model is able to replicate the same steps and get to the final answer, which is correct. If we think about the benefits of chain of thought prompting, one thing is that since the model is outputting the way that it thought and like the reasoning steps, we can easily debug. We can easily ask questions from the model and say, why are you saying this and this? So it's easy to debug. And again, it helps the model to decompose complex problems into small problems and solve them individually. Here also, there are some examples on few short chain of thought. So you can give examples of the exact same question type you are going to ask, and it is able to output the correct answer. And it turns out to be, you just need one example. So even with one example of the same type, you can get the correct answer. Then this is something interesting, and I've been using this idea like when I'm using ChatGPT also. This is called zero-shot chain of thought. The difference being like, so if we take few-shot prompting, we give a question, we give an answer, and we ask another question. It gives a wrong answer. In few-shot chain of thought prompting, we explain the steps, and it is able to give the correct answer. In zero-shot prompting, we don't give explanations or any examples. It gives a wrong answer, but by just adding this sentence of let's think step by step, you can get the model to reason and get the correct answer. So this actually works really well. Might be very helpful in the day-to-day life also. And in the paper that chain of thought prompting was introduced, they have tried to list out the observations in three categories, basically arithmetic reasoning, symbolic reasoning, and common sense reasoning. So if you take a look at the chart, with standard prompting, when you scale the model size, the performance seems to be a very flat curve. But with chain of thought prompting, with the model size increases, the performance increases substantially. So if you were to walk away with like one fact from this section of chain of thought prompting, I think it's that successful chain of thought prompting, it's an emergent property of model scale. So only after model sizes of 100 billion parameters and more, you can get really good results with chain of thought prompting. Next up, common sense reasoning. Here, if with standard prompting also, it increases the performance with the model size. But again, chain of thought prompting is way better. and its best performance is in sports understanding. So in the paper, they had mentioned that they compared Palm 540 billion parameter models performance with the unaided sports enthusiast, and they found that it's performing better than him. And again, symbolic reasoning, pretty much the same thing. Chain of thought prompting, and when you scale the model scale is increasing, it performs better. So it's again, chain of thought prompting is an emergent ability of model scale. So we couldn't have done this with smaller models. Then this is something recent, like in 2022, about automatic chain of thought. So chain of thought, it requires some manual work. We have to handcraft effective and diverse examples. With this paper, what they're trying to do is, when you provide a data set, they try to cluster questions into different clusters, and they will pick a representative question from each cluster, and they will use zero-shot chain of thought prompting to get the reasoning steps. So we don't have to provide the reasoning steps and everything. They will just get the let's think step by step prompt to get the reasoning steps. Yeah, that's basically it for chain of thought prompting. If you have any questions.
I don't have any questions for Suveen.
I have a question about the paper, because the paper was saying that chain of thought only happens on approximately 100 billion parameter models, right? Correct. There's another paper, the chinchilla paper, right? So you can have a small model that you train on more information, more tokens, right? That you can come close to the bigger parameter models. Does what they've learned in the chain of thought paper apply now still, or can a smaller model do just as well chain of thought?
I'm not actually sure. Like maybe if someone else.
Yeah.
Maybe I can try to answer your question. So I feel like number one, because for Palm 540B, right, I don't know whether it's. Well, I know it's after the chinchilla paper was released, but I don't know whether they follow the chinchilla scaling laws. So that's one. And then the second point is that your point about your second question was about asking about whether it still applies, right, for smaller models, right? So a lot of small models nowadays, like Hugging Face, right? Actually, what they do is that they actually fine-tune like foundational models like Llama 13B and 7B, right? They fine-tune that on like a very, very well curated data set. So for example, a recent paper like only 2 weeks ago, like Platypus 2, right? What they did is that they fine-tune a very high quality subset of like GPT-4 completions, and they actually allow it to improve over Llama 70B, I think, yeah, on the Hugging Face leaderboards for I think the science Q&A data sets. So yeah, I think yeah. So I think really the key point is really like how good your data is as well. Yeah.
So there's two things, right? The quality of data and the number of tokens. I think Llama also was trained on 1.5 trillion or something. So it's good. Yeah.
I encourage you guys to take step. Yeah. Okay. Like how would these models be able to do this task? Right? What would get it to be able to do chain of thought anyways? Right? Why does asking like let's think step by step actually help? And why would it be the case that having a larger parameter data, higher quality data, allow it to complete it? You guys answer that question. Take step by step. Like what are reasons for why that so-called emergent, I question that myself, a property comes about. It's a complex task. Context.
So like, let's say, right, you don't generate this chain of thought.
Right.
You already have this, right? And then you put it in a model, it will do the same result. Yeah. So you don't have to go step by step. You can create your chain of thought for them.
Right. When the model is not asked to do step by step, right? It's trying to go directly to the answer, right? It's using its math language model to say, okay, well, what's the next token? The next token is the answer. Right. When you're asking it to do step by step, it has to reflect about all the other instances in this training data, which it has all step by step, right? And it's just generating all of these steps outward, right? But while it's generating its output, it's auto-regressive, right? So it's also thinking about what it's generated already to figure out what's the next step, right? So why would it actually work? It works partially, I think, because when it thinks step by step, it has to have enough data for those individual steps. in its past history of training in order for it to generalize, right? So if you don't have enough data of that quality that helps you explain those individual steps, then it falters, right? But so it'll come up to a step where it's like, oh, I don't know I don't know how to do this step. And so step by step breaks down, right? But because, going without the step by step, when you're just generating the answer directly, then the language model has to do all this internal reasoning, but it doesn't have anything to grasp on. There's no handles to scale the wall to get the correct answer, right? So this is why thinking step by step helps. And this is also why you think when you do something like zero shot chain of thought or just chain of thought in general, why that might help, right? Like asking it to think about it would say, break the task down to another task that it's seen before, right? And it can do this task individually, right? So if you have a complex task, but all of those atomic tasks are really easy, and those tasks that's been seen before, then there's a lot more chance they can complete it, right? It's compositionality, right? And being able to generalize those ones. Okay, so I want you to, again, think about like the distribution of data, okay? Why would high quality data or more data help? Okay, like if I'm thinking step by step, where does this data come from? If I see steps, where am I going to get it? Right, like for example, if I have a data set of cooking recipes are step by step, right? You don't say, here's how to bake the strawberry shortcake, ta-da, you're done, right? Good luck with that, right? You have to go step by step. So having those steps will make it easy to do, right? So you have to generalize to like, what types of data are you feeding it? Are you feeding it data of numerical form, or there's step-by-step demonstrations somewhere in your data set, and they're high quality enough? Okay, maybe that will help figure this out. Okay. So again, in your own mind, try to think like, why would these things work? We know they work, but that's not the whole point of the class. The class is like, why do they work? What are we not doing to make it work better, right? Because we want to think like these researchers, like this Japanese paper from our associates at University of Tokyo, like Matsuo Sensei. He's come to NUS before, by the way. Anyways, his paper said, just insert this one phrase. Let's think step by step. And now I want you to reason about why that works. Why is this trick so useful? Right? So now we know, right, in part. Okay, but there are other tricks that are not discovered yet. Okay, and we are here in this community to try to figure out what it is. Okay, look at the data, think about what it's trained with, think about what you want in your output, and then engineer a prompt or a tunable method using gradient descent and backpropagation to get there, right?
Is there any other questions for chain of thought?
Okay, that's thanks, Suveen.
Okay.
I move on to Lawrence, who present about self-consistency as well as tree of thoughts.
Yes, hi. I just introduce myself. I'm Lawrence. I'm an external guest from a company. I'm just a new startup called Humani.AI. It's human intelligent amplification using artificial intelligence. So anyway, okay. So the reason why I joined this is I want to brush up on what we do. We've been using GPT for like 3 years now. So and it was GPT-J in those days. It was horrible. Okay. All right, cool. So today I'm going to talk about self-consistency, but also maybe a jungle of thoughts. Okay. Oh,
this one answers.
You want to move that? Okay.
Oh, someone made a question. Prof, do we?
Okay, yeah, so
Okay,
maybe we
answer that.
just pause for a second. So shall you ask, is there a soft benchmark on how many minimum parameters are needed to do chain of thought? So do you guys have an answer? What do you think?
So in the paper, they say the emergent property comes after 100 billion parameters.
100 billion parameters. Okay.
That's like, yeah, that's like the soft benchmark.
Okay, 100 billion, but I think correlated to that is what? That's the size of the model, right? What other things are
between
the quality and the quantity of the data, right? You have 100 billion parameters, but you have one training example with
That's true.
Right? So it matters on both sides, right? You need a sufficiently model with sufficient capacity to represent the data. And you need to have the quality of data and the quantity of data to make sure that the parameters are set well. Right? Yeah.
Here's a quick add-on is that they also say that the time of the compute for the so-called flops is also very important. Like you need to train multiple times on the data. So it will also improve a little bit. So it's just like a triangle, right? So the quantity, quality, and the compute have to satisfy the three angles.
Yeah, again, you can think about it yourself. So everyone on the scribe team, again, think about these questions. You can note it down in the document. Doesn't have to have an answer. You can just leave it as an open question. Okay, but do documents just so that we can have something.
Okay.
Okay.
Okay, sorry. Thank you. Okay, I must apologize. My slides a little later. I started on the work yesterday lunch. Yeah, I was busy on weekend, and I literally had to digest 12 papers. And finishing up the last paper around 6 o'clock in the morning. So the last paper is not that great, but anyway, do excuse that. So I just don't talk about jungle thoughts. So let's go about stuff. Up down.
No, left and right.
Oh, left. Okay. No, okay, there we go. Okay, good. So what is self-consistency? This is a Google Brain team project. It's about an advanced prompting technique that builds on the chain of thoughts. The aim here is to improve the over what's using in the COT using greedy decoding by using a different method to give you most consistent answer. Okay, and the paper is actually given there. That paper I read, I don't know, 6 times. Okay, so I just want to keep it simple, not too much maths, but just simple. What is self-consistency? So in real life scenario, human beings, when we think about different reasoning, we will look at various paths to come to a decision. So in self-consistency, we want to simulate this process. We provide a model with a couple of different perspectives and directions, and then encourage you to evaluate in a critical manner, and just to get a very likelihood of a better, accurate, and unbiased response. This is also important because I think that when you do 0 shots and 1 shots, you don't get you get an answer immediately, but you don't know why. So there's a push towards what's called XAI now, the explainable AI. Most AI are black boxes. You put something in, you get something out, you have no idea what it does. So what we want to do is see whether we can use this to our advantage. So diverse reasoning paths and self-consistency. So human thinking versus language model. So we think in different way because we're self-prompted. Humans are self-prompted. Okay, we can look at different direction of path. Sometimes you try one thing. They say that insanity is doing something over and over again, expecting some result. Okay, but most humans luckily are not that insane, but most AI are. So so we keep doing the same thing and get same results sometimes. So self-consistency model, we begin with a chain of thought. The COT example as a prompt. We want to generate diverse candidates reasoning using sampling techniques, changing the temperature, the top K, the nucleus, etc. And then we aggregate the answers by marginalizing the path, which means basically we ignore the least popular ones and we pick the most popular ones as the final. I'll give some examples later on as well. Okay, and the maths at the bottom, talking about variable of RI, which is the reasoning path. Yeah, okay, and the AI as the most consistent answers. Get more clearer a bit. So how consistency works is we have 5 things we need to do. We need to identify the problem. So defining the problem, the question you need to answer. We need the LM to answer. Make sure it's clear, specific. Then we need to create multiple prompts. Now, we develop various prompts to approach a problem from different angles. So remember that in a COT, we basically have things step by step, but you're only giving it one particular path. It's a forward path, right? There's no sideways, like this is the way to do it. What we want to do is make it so they have variable paths, multiple paths, and each path we need to adjust something, and that something is basically the temperatures and the top K, P, and so forth. Okay, so then after we generate response, the tree just generate response, and then we evaluate consistency. Consistency means that you generate several answers, and then you look at the answers and you say, well, most likely is the one that the right answer is the one that generates most often. Okay, some will be wrong, and majority wins most of the time. Okay, by selecting the best response. So the LM's reasoning ability is limited, but enhanced only by skill. So if you look at this chart here, so there are, if you look at the top part, in the COT, you basically get a prompt, go to a language model, go to greedy decode, and you get an answer. And you can see in this answer, it's wrong. Okay, which is only one way to do it. Now you may try this a few times, and occasionally it will work. You get it right. I've tested it before. Sometimes you get this answer, and sometimes you get, I don't know, some rubbish. But you know, it's luck. So here, same thing will happen with the self-consistency is what we do, same thing. But this time, you notice we have 3. We can do more, but let's say 3. And here, we have 3 different sets of answers. We marginalize, we vote to the most common answer. Okay, so the more path you take, the more consensus you have, the better your result will be. Okay. So consensus method precepts, you prompt the language model using the COT. You replace the greedy decode by sampling from the model's decoder to generate the double set reasoning paths. Then you marginalize out the reasoning path and aggregate by choosing the most consistent answer. Okay. Simple, 1, 2, 3. Okay, and we have some results here. This is samples on 2 questions, and one using decode, greedy decode, and the sample path 1 and 2, which is the ground truth. You find that the answer is more consistent. Now, again, this is following the same COT rules, right? Giving it enough examples and steps to do it. Okay, so consistency we call prompt recipes and templates. Now, incorporating the method is quite straightforward. You basically give example elements, but in a new element, you only need 1 or 3 examples to get the results. Okay, and later we'll see there are some better methods as well. I will give some examples here, some snapshot of some arithmetic reasoning. Okay, again, it's taken from the paper. There was a lot, but I just picked the first 4 or 5 of them. Okay, same thing you do NLI. You know, the premise, give an option, because we give it a few examples, like, you know, multiple choice question, pick one. Okay, and you'll pick the best one. And again, few short examples for Aquaret. Again, multiple choice questions. Some will be more complex. In fact, I find that now the new tuning I tested on GPT-4. By the way, and when I read through the papers, I literally test everything out. That's why it took so long. Okay, so except for the last one, which at 6 o'clock in the morning, I'm like, okay, no more battery. Me. Okay, the advantage of evaluation self-consistency. Now it's simpler than most other methods. No extra training, no fine-tuning, and it's just avoid the issues of repetition. Okay, it's improved accuracy. Okay, and you get more likely to get the result of the correct order. There's reduced biasness as well, because remember it's consensus. You're having various outputs, and you just pick the ones that is the best ones. The more or less, you know, are the same. Enhanced critical thinking. Okay, now this one acts as a self-ensemble. I want to use a very simple analogy. It's like, imagine you have an orchestra or one person using a violin. Now, you actually get violin, you can play 3 things. You can bow it, you can strum it, you can bang it. So you have a drum, a guitar, and a violin. Okay, so some ensemble. Okay, a full ensemble will be like various instruments and various models. So this is one model, but because you leverage different settings to that model, gives you various results. Okay, evaluation is done on the various model, UL, unified language, the GPT trees, and you can get really good scaling. Excuse me. And self-consistency is also very robust because with multiple results, the average out the issues. Because what happens is sometimes, people make mistakes. They type in and you get issues. And so what happens is that you can look at also an interesting thing is the temperature setting. Now, because you would think that the low temperature setting is more accurate, it's actually the other way around. Because you're giving more variable, it gets more creative, and you have, more variety of answers. And of course, and you look at again same thing, like how much parameter model you need to get a better result. And in fact, it improves a lot, right? Okay, as the bigger the model gets, okay, self-consistency actually gets better. We call this the COT SC, okay, for short. So robustness is also there because, as I said, people make mistakes. And even if you make mistakes, somebody spell it wrong, or you have some of the actions reversed, it still works. In fact, the accuracy jumps quite a bit, up to 17.1 for COT, and your self-consistency jumps at about 23. Oops, sorry. And we'll see some more of that as well. Yeah, up to 69 with 40 paths. Literally means 40 different varieties of answers, and you vote about the best ones. Now, here is something interesting because this is a comparison of 3 thoughts against other prompt strategy. This is a project by Google Mind, Princeton University. Now, on the left-hand side, we will talk about a simple I/O, which is the 0 shot. Give it give the question, gives you an answer. That's it. But then in COT, we have a thing like think step by step. So it works out. Each box is a thought. Okay, we call that a thought. So in self-consistency, we have several streams of thoughts, and we vote. Okay, all right. So the COSC. And the idea is that, why don't we make it into a tree where now we have not just forward-looking path for the thought, you also have sidetrack. So multiple, I call experts, by the way, this is why I say an expert. Okay, we call each path an expert. Okay, and now you'll see that later on in my prompts, we actually set it up. And then you will backtrack until the problem is solved. Okay. So this is what's called tree of thoughts. Okay, it's an improvement over the self-consistency core model. Okay, so we want to solve, human beings solve problems again, resembling searches through tree of possibility. Because remember, just now we had the self-consistency model. Basically, you only adjust the temperature, top P and K and so forth, right? Here we do it different way. Okay. So with the components of thought, now there are about 4 of them. Thought decomposition, we break down the problems into immediate steps, make it description and equation. So thought generator. So what are the next steps going to be? Potential next steps. The state evaluator, quantify, beautifully, And the last one is basically we look at whether it's going to be a breadth search or a depth. Okay, how wide and how deep. So why this tree of thought? So both the core SC and the React, which is the next one paper actually, often require the decorating of a base question. Okay, now decorating, by the way, the word is means that you're generating a specific prompt template, a style of prompt. Okay. It's the base question to simulate the emergent property of LLM, just to get quite a new skill at inference time. So so this is developed into a framework like LangChain. It's a very popular framework. I'm sure you're familiar with it. If not, have fun with that. There's a lot of useful tools inside. So there's a series of modules that store the next text for decoration of the base queries. So thought or tree of thought is a technique specifically just to mimic human brainstorming method and collaboration. Okay, it's very well suited to mathematical reasoning, in particularly linear algebra and logic. So here's an interesting example of a thought prompt decorator. Okay, remember the first step, you have think through each steps logically. This is taken from the COT example. Then we add few more. Now I've colored it differently so it's easier to read, right? So imagine there were 3 experts. We can more, but let's use 3. Okay. When answering these questions, they will brainstorm the answer step by step, reasoning carefully and taking care of all the factors in consideration. Each of the experts will write one step of the thinking and then share with the group. So the sideways, right? Getting the prompts to read each other. They'll each critique the response, and with all the response of the others, they'll check the answers based on the science and laws of physics. Okay, which means this expert has to be experts of laws in physics. Okay, the expert will then go on the next step, which is the next, and write down each step of the thinking. They'll keep going on each step until they reach the conclusion, taking into account the thoughts of the other experts. Interesting, right? Like people. If any one time they realize there's a flaw in logic, they will backtrack to where the flaw occurred. And if any one expert realizes they're wrong at any point of time, they'll acknowledge it and start another train of thought. Or you can even say it ends. Okay, up to you. And each expert will assign a likelihood of the current assertion being correct. Continue until the expert agree on the single most likely location. In this case, the reason we put location is because of the problem. It could be a solution. And the question is. So this is a very long prompt. Okay, but it's an interesting one. I'll give you a case example. This is an example. Carlos is at a swimming pool. He walks to the locker carrying a towel. He puts his watch in the towel and carries the towel tightly to a lounger at the poolside. At the lounger, he opens and shakes vigorously the towel. Then he walks to the snack bar. He leaves the towel at the snack bar, then walks to the diving board. Later, Carlos realizes he lost his watch. Where is the single most likely location of the watch? Now, this is a detective story, right? So if you read it, the first thing you think is, I need to think about this. Where is most likely? You look at each of them, and in your mind, you're doing the same thing. You try and infer, it's not likely the number 1, and it's not likely number 6 because it's already lost the watch. Okay, so anything between 2, 3, 4, and 5. So when we run this case through GPT, this is 3.5. I ran it last night, and this without any prompting. Just give him the question and hope to get the answer. And it gives you an answer, but it says most likely it's a snack bar where the towel is left, and it gives some sort of explanation. But when you read through it, it's like, I don't know, man. It's not quite correct. Okay, it may not be. I'm not convinced. Right, I'm not convinced. So using that TOT prompting, we get this. It's a bit large. Now again, I've color coded it. Expert 1. You notice it's created a physics expert. Remember, we talk about laws of science and physics. Okay. And so it says, okay, Carlos is simple, right? And it's a critique and feedback as well. It actually states that. All right. This step seems accurate, likelihood 95%. So it's created, okay, the actual result for that. And expert 2, forensic expert. Oh, interesting. This is a detective story. All right. He walks in the locker carrying a towel. Now, it's a different task now. This is task number 2, right? The second step in the color story. Then the feedback is that it's reasonable. It aligns with the common behavior of the swimming pool. Likelihood 90%. Number 3, behavioral psychologist. Interesting. He puts his watch in the towel. So that means there's someone wanting to secure belonging. Now this means logical. Yeah, tightly wraps it. 85%. So now it looks back. Now expert now looks at the other results and says, since I can see the other guy's result, I want to take a look and see whether it doesn't make any sense. So it's critiquing the other results. And then it says, well, is my result better than his result? He's more likely. So the likelihood now is that potentially the shaking of the towel could cause the watch to fall out. If it's not secured properly, 80%. Expert 2 now says, let me look at the others and say, well, okay, but he abandons the towel at the snack bar. So maybe there's a potential moment when the watch could have lost. 75%. It's not so sure, but it's not give it some scoring. And number 3, the behavioral psychology says, this is most likely place is because maybe when he opened his towel and shook it vigorously. Again, remember, it's similar to the self-consistency when you vote on things, but now you not only vote, but you critique each other before you finalize the result. Okay, and you can repeat it several times. And then it comes to final conclusions there as well, based on the collective analysis, most likely the patient is when Carlos opened the towel and shook it vigorously. Its conclusion takes place on account that the physics and a potential item displacement during shaking, the behavior of the secure belongings in the towel, and possible moment of loss when transitioning to the snack bar. Overall, like 80 to 90%. It's taken 80% from expert number 1 and expert number 3. They combine together and gives you the most logical answer. Okay, interesting, right? This is a very complex problem, but it's very useful problem. And I'm
just one point of order.
Okay.
Because it's 5:08, anyone who needs to leave, you're welcome to go. I mean, the session will be recorded. I know that Lawrence is in the middle of this segment, and then Lawrence still has a segment. We try to see whether we can get through most of the things by 5:30.
okay.
Okay.
Great.
Yeah.
Thank you. So I gotta speak faster.
So you might want to skip some examples.
Okay, sure. Well, it's a game on. I'm not actually doing this one. Just give an example. That there's a game of 24 about this. And you can find on the network, and there's a couple examples you can see here in terms of the thought evaluation and the results. And you will see that the jump is interesting because now it's just a consistency of 9% from 7.3. It jumps to 74%. It's a huge jump. Again, as long as the breadth is very wide, B equals a 5 and B equals a 1. Okay. And again, some reasoning difficulty, basically what are the issues on this one. So you can read about it. And the success rate compared to the others for the game of 24, it's a game basically you try to figure out the 4 numbers, 1, 2, 3, 4. Well, how you multiply gives you 24. Okay, or add or plus or minus whatever. Okay, so benefits of TOT is it includes prior approaches. It includes the IoTs, the IOs, the COT, the COTSCs. It's also modular. Okay, so accommodates a variety of the various platform, and use only requires a pre-trained LM without need to extra training. There's no fine-tuning required, and it's also robust like the self-consistency. But here's the question: is if you look at the TOT, it says it's only one particular branch. It's one tree. What happens if you have a forest of dots? Interesting, right? So this is a example of the we're using LangChain template. You will see the LangChain itself, there's a lot of modules. The rest of the charts are there. So we talk about decorated prompts. So like the one we just did just now, the detective version. Okay. So in this example, we can use that in the Python code. You can put the templates right there and the questions, and then you can fire it up and you get a result. So the idea is that you could have literally 3 sets of trees running with variable output. So another question is, why limit ourselves to the same large language model? Why not use different models? Get more variety. The more variety and the more diverse viewpoint of the same problem, how we approach problem is better. Well, sometimes you're stuck in a problem, you go for fresh air, some people for smoke, some people for coffee, and then suddenly, oh, new insight. You come back and you look at the problem again. All right. In this case, we use different language model for that, and we aggregate the end using a GPT-3 aggregator to get the result. And again, in LangChain, it allows you to do that. You can add as many language models as you like. So you literally can have a forest of thoughts. And you can try out different Hugging Face models. Okay, let's go there. Now, this paper came in, like I just said, 5 or 6 o'clock in the morning. This paper is about 2 weeks old. So ETH, it talks about a different item, which is basically the graph of thoughts. Now, I've only gone through half the paper, but I'll give it the first half. The same thing applies in the beginning, the IO, the COT, SC, and the tree of thoughts. Okay, you can see all the different branching forward, sideways, and this is erased because, the result was no good. Okay, and you get a final result. The idea of the graph of thoughts is very similar to the tree of thoughts. The only difference is that it actually not only backtracks, it also refines itself. Oh, sorry. It refines each output itself to get your results, and it aggregates the thought at different times not at the end, but on at different junctions. So what I got again from the beginning of the paper was the transformation is more human-like than TOT, a bit more human-like. And it's about 64% more accurate than TOT. And it's about 31% less reduction cost in terms of compute time. And there's some example, they were testing about 64 numbers. Again, I've added all the resource links at the end to read the paper. Okay, and there's a couple of graphs. I've gone through this part, except, there's a lot to take in. All right, I just put in there for reference. So the last part is to talk about is how do you evaluate the performance on tasks versus databases, and there are a couple of benchmarks you use, Diana bench as well as big bench. Okay, just to see how good is your, model doing. Okay, resources are here. You check the COTs, the original paper. That paper is in 2022. Yeah, 2022. The three thoughts are a little bit newer in this year actually. In fact, the last one would be the forest of thoughts. Again, we talk about the forest of thought as being multiple trees, and that's a GitHub actually, so you can have fun with that. And the last one, of course, the graph of thought, which came out like 2 weeks ago. So also they have GitHub. I haven't gone through all of it. Okay, that's all. Thank you. Any questions, please?
First, let's thank our speaker.
Okay.
Any questions? Yeah, I want to spend just 1 minute helping you think about this. I mean, we have gone from chains to trees to graphs. What's after graphs? Okay, big step by step, right? All right. The other thing I want you to think about is if you've taken an AI module, you may have done A-star search, right? A-star search means you have an H of X and a G of X and an F of X, right? So you search forward, you search backwards. And so we haven't really talked about thinking backwards, like thinking from an answer and reasoning step by step backwards. But that's also possible, right? And you've seen a lot of movies where, a character makes a key decision and it's a life-changing moment, right? And you can think about that in terms of like reasoning. Like there are some things like in a game of Go or chess, right? You make a key strategic mistake, the game is over, right? And so for those types of key reasoning steps, you want higher temperature, right? Like I think Florence is saying, because you want to look at all possibilities. You don't want to think just sort of at the normal part, because then there's some difficulties in getting a good output from that. Okay, so this space is still very ripe for exploration. You can see that there's still a lot of things. Maybe there's manifold of thoughts or whatever you want to say, continuous thought rather than, discrete space thought, etc. Those things are probably in the making. And, there are people in this room or people online that could be a part of that association. Okay, so I think Warren has the last part.
Okay, so for my paper today, we'll explain more about React or synergizing reasoning and acting in large language models. So what do you think of when you hear the word React? A lot of software developers, right, will naturally think of React.js, which is a web application framework. However, today we're talking about React, the AI paper, as a paper by Princeton and Google. So what exactly is React? React is a prompt engineering technique that aims to get large language models to reason and act the external environment using APIs. And it consists of 3 parts: thoughts, action, observation, that I'll go through later. First, I want to explain why the authors actually created this paper. So why React? This is because it provides the language model the ability to query and interact with its environment through prompting. And this is not widely researched at that time. At that time, only single papers like Inner Monologue and WebGPT, but nowadays there's more agentic large language model papers like Voyager and Bola. So that's one point. And the second point will be, it also updates the model's knowledge base through the use of APIs. And this is something like retrieval augmented generation. And this will allow it to hallucinate less and have less error-prone completions. So this is an overview of what React is. So for a single prompt, you have these multiple thought action observation triplets, which I call trajectories, and you use this multiple times before it and to guide it to the final answer. And in order for the language model to actually understand this React format of this thought action observation, you want to give it a few short examples in order for it to understand the format as well as the APIs used. So I'm going to break it down to the individual components and explain more about them so you have a better understanding of what React actually is. So firstly, we talk about thoughts. So React thoughts are like basically an inner reasoning of the large language models, and it allows you to decide what steps to take. So for example, right, for this question where you want to what other things can substitute Apple Remote, the images here show like multiple steps that can be taken in order to, as steps in order for the language model to arrive to the final answer. So for example, thought 1 will be like, I need to search for what an Apple Remote is. And that brings us to our actions. So an actions is the actions taken by the large language model after a thought, because a thought is a step. And this step allows it to bring it to a certain place, but then you still need to call an API in order to, or action in order for it to understand or more about like what the Apple remote is. So for what I mean by that is like, for example, if a thought here that says I need to search for Apple remote, the action actually executes the action. So it actually calls a Wikipedia API to search for what Apple remote is. And in the paper, the authors use a Wikipedia API exactly for this reason. So an action will search for a certain subject using a Wikipedia API, and then that leads up to a final component, which is the observation. The observation is the result from the API. So after the API call, what's the result? The result is not the observation. So why do we need this observation? It's very simple. Because after you have this observation, right, this you can use in-context learning to generate your next step, which is your next thought. So your thought number 2 will be generated by the observation, and so on and so forth. So what do I mean by this? That it's a more high-level view. You can look at the right-hand side, which is like multiple thought action observations until you reach the final answer. So thought 1 will be like, what's the first step I need to take? And then from that step, I need to search for Apple remote. Then after that, using the information retrieved from the API, I use that to formulate my next step, which is that we know the Apple remote is originally designed to control this kind of media program. But then now I need to search for what else we can do with the media program. So it does this like step by step all the way until you get the final answer. And so it converges the answer to that. So now that you know what's React, right, I would like to ask a question to the audience. As you can see on the left-hand side, right, there's reason only and act only. So why is it that these two are ineffective compared to combining both together? Does anyone have any guess on why that happens?
Repeat your question.
Oh, sorry, too fast. So, so on the left-hand side, right, there's like reasoning only and also acting only. So why is it that both of these are like inferior to both reason and acting together? So if not, does anyone have any ideas?
Yeah, educated guess. So
Okay.
when you're actually, for example, you're searching, you have more information from the web.
Yeah.
Is this answer correct?
So I think it's somewhat there. It's somewhat there. So, but the thing is that it answers why it's actually better than reasoning, but it doesn't answer why action fails. So I can actually go into that. So for when you do reasoning only, what happens is that you're only prompting using the internal representation of the model. So the internal knowledge of the model is being used for chain of thought. And sometimes when you train the model, the data can be biased or inaccurate. So what do you mean by inaccurate? You can train a model with 2012 data. And then when you ask it, what's the current president of the United States, it'll give you Obama. However, we know that the current president is Joe Biden. So that's why we're inaccurate. And biasness is like, sometimes the data can be very biased. And because of that, it will give skewed answers. And this may not be what we want. So that's why chain of thought only does not work. For action only, you can think of the analogy of a toy robot. So the robot can do a lot of tasks. However, there's no higher purpose of why it's doing these tasks. And there's nothing to guide it to actually get to the final answer. So that is why actions may not converge the correct answer all the time. But by combining the internal knowledge and the internal logic of the large language model, as well as the ability for it to generate and also pull data from external outside APIs, it's able to combine both together, and that's why it's more superior. Because it's combining external knowledge alongside the internal reasoning of the large language model. That's why it's much better. So now to go on to the results. So this is a preamble that shows the settings the authors use for the React paper. So the authors use Palm 540B for the evaluation of prompting strategies. And then over here, they use 4 data sets called Hotpot QA, Fever, L4, and WebShot. So I'll just explain all 4 of these first. Hotpot QA is basically a question answering data set, and use it for question answering evaluation. Fever is the fact verification data set. So it will be like something like they'll give an opinion, and you have to verify whether that's a fact or that's an opinion. Then for L4 and WebShot, these are more environmental-based data sets. So they give you an environment to play with. For L4, it's like your terminal-based games like you saw in the 1980s, where you control using words, right, to control a character and move him around. Then for WebShot, it's a more real-life scenario. With a website, you can navigate through the website to find products. So my question to the class is, why do you think they use these benchmarks in order to evaluate their model or their prompting strategy? Does anyone want to make an educated guess?
Welcome to reason down.
Let's think step by step.
Because the data, because it's not updated, and so having ability to query and compare to fresh data.
Yeah, that's actually one of the points. Does anyone have any other guesses?
If I'm not wrong, at least from what I know, some of these benchmarks, they are multi-step. They are multi-step benchmarks. So that's where you can see React shine because it's all about multi-step. Like
Yes.
for example, hot QA, if I'm not mistaken,
Yes,
viewing at least 2 different Wikipedia pages.
yes,
Is that
correct.
right?
Yes, correct. This
Yeah,
multi-hop.
so
yeah.
so there are steps in there.
Yeah. So actually, both these answers are very correct. And just to show like a full explanation, the first one is like to show robustness across various tasks. Like the authors wanted to show that this is a very general prompting strategy and it's not constrained to only high performance on only one single downstream task. So the second point is what Nicholas and what Lawrence has said. So they wanted to show that being able to retrieve external knowledge was crucial for LLMs to reach better results. Because on all these multi-hop data sets, right, by being able to query the external API, right, it will allow it to actually perform better. Then the third thing was also for L4 and WebShot, which are environmental-based data sets. They also want to prove that having this higher level of purpose or this reasoning alongside actions is very important for these kind of environments, because then the LLM will be able to reason out why it's actually doing these tasks and guide it to complete the task correctly. And lastly, because WebShot is like a website-based environment, right? The authors also want to see how React can directly translate to real-life tasks. So therefore, they tested React on noisy real-life tasks like WebShot. So now I'll go more to the results. So firstly, I'll explain like the image here first before I head over to like all the insights from the results. So on the left-hand side, you have this table which shows the different prompt methods the authors use. And then over here, you have this thing called EM and accuracy in the benchmarks. And basically, the thing you need to know is that for both these numbers, right, the higher it is, the better it is. So therefore, you can see like COT SC arrow React arrow COT SC, right, is performing the best on like both of these benchmarks. And I'll explain more about what they actually mean later. Then on the right hand side, you have some of the graph, and I think it's because the authors also wanted to test out on self-consistency. So they had multiple, the x-axis is like how many self-consistency trials they actually use, and the y-axis is the performance of the model on like both of these benchmarks. And what they found out is that there's actually, after a while, right, self-consistency actually plateaus, but it actually does help improve performance for a while. So now I'll go on back to like what the results actually mean. So firstly, it shows that by actually combining the chain of thought hybrid, the self-consistency as well as React, that's actually superior to other prompting methods. And then what does React chain of thought SC means? It just means that chain of thought is a fallback strategy. So if React fails to converge to the answer, it will change to the chain of thought prompting strategy instead to try and get the correct answer. And then for chain of thought to React, it just means that if less than n/2 is the majority answer, like what Lawrence said, chain of thought self-consistency tries to prompt different ways, and then like it gets the majority answer. So if less than n/2 is the majority answer, right, it means that the model is not confident that this answer is correct. So you use React instead to try and reason it out. So the next thing is more of the limitations of React. So the authors ran further studies on React versus chain of thought. And they found out that hallucination is a serious problem for chain of thought. And over here, I've actually marked down the results over here. So you can see my mouse, right? 1, 2, 3 actually corresponds to all of the different like data you can actually take the insight from. So the next 2 points are more like related to React. But firstly, they realized that this interleaving of reasoning and observation, or this thought action observation, is actually detrimental to the model's reasoning flow. So because this forces a structural constraint on the model's way to reason, and then sometimes this breaks the reasoning flow of the model, and therefore sometimes it reasons stuff wrongly. And the last thing is also successfully retrieving like useful information from the API is also very important, because without this, right, you cannot perform in-context learning, and therefore what happens is that the model actually is unable to guide itself to go to the correct answer. So those are some of the limitations. And one more limitation here is that the authors want to see whether, like for React, right, whether this is model size agnostic. So that means if you use it for smaller models, will it have the same impact? And the answer is no, because after 540 billion parameters, it's actually the best performing prompt strategy. But actually on like smaller models like 8 billion and 62 billion parameters, it performs the worst. But like a key takeaway is that even though it performs the worst on smaller models, when they fine-tune on completions of React, and what I mean by this is that they take the 540 billion parameter model, and then they run like the input prompts through that, and then use the different prompting strategies to form the labels. Then they train a smaller model on this input to the labels. And they found out that when you do this training, right, React converges the fastest. So on a React fine-tuned smaller model, right, it can actually beat bigger parameter models like 62 billion vanilla Palm. And the 62 billion parameter vanilla Palm can actually beat 540 billion parameter vanilla Palm. So actually that's a very cool insight. And the last part I want to talk about is using React's agentic framework, because now agentic large language models are very popular nowadays. So on L4, React actually outperforms Act, which is just Act without the React without reasoning. So there's no reasoning involved, just actions only. As well as Butler, which is one of the state-of-the-art imitation learning models at that time. And then on WebShot, they found out that one-shot actions only without any reasoning actually can perform on par with imitation learning models, which were still at that time. But React performs significantly better than both of them. And it's more likely to find products that are more relevant to the problem through reasoning. So they also study like similar work, but I won't really go much into this because it's actually a bit different from each other. All you need to know is that inner monologue is like a very simplified version of React, and React has much more better reasoning traces. Like it can decompose tasks better and also have more common sense reasoning. Like for example, a normal human would think a microphone will be on the table, but then in IM or inner monologue, they don't have this kind of reasoning to kind of reason it out. So they may also think that the microphone is like on top of the projector, for example. So React beats in terms of common sense reasoning. It can narrow down like where's the location of the microphone better in that case. That's why React is better than IM. And that's all you need to know about their similar work. And now really that's all of my lecture. And I just want to go through like some of the cool extensions of React, which is like there's now multimodal React that was I think released like this year. And just using textual description of image to kind of like extend React to multimodal transformers. And then the other two is more recent and really more cool, but they're not really relevant to React. But I just put them here because it's the same concepts. Toformer is a large language model that's trained to call external APIs by giving a data set of APIs that you can call, as well as like how to call it. And then by doing this, right, it's able to learn how to call APIs and when to call them. The last thing is something released by OpenAI like 2 or 3 months ago. It's called OpenAI function calling. And it's not really using React, but using a similar concept of having a large language model that is able to understand and call the function when needed. So yeah, if there's any questions about React, yeah, feel free.
Let's first thank our presenter. Any questions? We're all tired out, I think. Okay, so let's do our step-by-step thinking at home then.
Yeah. Just to conclude, I'll send these links to general, but there are additional resources you can learn to explain more about prompting. Yeah, and that's all. Yeah, that's really thank you.
All right, thank everyone for
That's fun.
Yeah, whoever's interested in the, just now we were having a discussion about like
Temperature.
Okay, my claim is that under some assumption, a probabilistic decoding model at 0 temperature can become deterministic. I'm not sure when is a good time to have a discussion because I know that something required. I don't know, but I would definitely like to have a discussion.
Okay, so if you're interested to talk with Nicholas now, there's a whiteboard in the front. We can do that, but it's offline after as the class is over.
Okay.
So please come up and maybe if you're interested to hear Nicholas can explain. We can start now if there's anyone interested. Otherwise, we can do it again. We can raise it on the general channel and see when's a good time that people want to discuss. Like you can ask, is there anyone interested? Like a poll, and then find a good time and explain it. Maybe that's better.
I mean, the key thing is like
I already said it, so I don't really matter. Yeah, because I already said that deterministic people should.
Yeah, it's the experimental. Yeah, no.
Okay, so why don't we raise it on the general channel, and then we'll try to find a good time for that. I think that's something that people want to know. Okay, thanks for all of you who are online. Have a great time. See you next time.
Or Jackson.